Hello and welcome to part 2 of the spin series. I'm Daniel Thompson and today I'm going to answer the question, does spin increase driving distance? So let's get to it. So in last week's episode I explained how spin is generated on a golf ball. So if you haven't done so already, please watch this episode first, because today I'm going to continue with this discussion and answer whether or not spin increases driving distance, and explain the impact that spin has on a golf ball. But first, I think it's important for us to understand the distances that are achievable off the tee, and the spin that is utilised. So let's look at the statistics of some of the biggest hitters on the PGA Tour. So when looking at the average driving distance statistic on the PGA Tour from last season, Bryson DeChambeau took #1 spot, with an average driving distance of 324 yards. And in second place was Rory McIlroy with 319 yards. But these athletes aren't actually the biggest hitters on this planet. So let's look at the two-time world long drive champion, Tim Burke. He hits drives over 400 yards. Now that we are aware of the distances that are achievable off the tee, we now need to understand the amount of spin that is utilised. So, on the PGA Tour last season, Bryson DeChambeau had an average spin rate off the tee of 2,584 revolutions per minute, and Rory McIlroy averaged 2,360 revolutions per minute. And when Tim Burke hit a 419-yard drive, he had a spin rate of 1,850 revolutions per minute. Furthermore, when you look at the average spin rate on the PGA and LPGA Tour off the tee last season, the average seemed to be around the mid-2000s. So as you can see, when an athlete is trying to hit the ball a long way, they utilize a spin rate that is in the thousands. Now let's just think about this for a moment. Do you really appreciate how fast a spin rate in the thousands is? So let's put this amount of spin into perspective by looking at things in society that rotate. So I've selected 3 things for us, the first being a wind turbine. Now the blades of the wind turbine rotate at around 20 revolutions per minute. The second thing being a helicopter, and the blades on a helicopter rotate at around 400 to 500 revolutions per minute. And finally, imagine a car travelling on the motorway at around 70 miles per hour. And if you think about the tyre on the car, the tyre will be rotating at around 1,494 revolutions per minute. As you can see, these spin rates are lower than the spin rate on a golf ball, with the average spin rate on the PGA and LPGA Tour last season being around the mid-2000s. So the golf ball is spinning around 125 times faster than the blades on a wind turbine, around 4 to 5 times faster than the blades on a helicopter, and around 1.67 times faster than the wheel on a car traveling at 70 miles per hour. So as you can see, the spin rate on a golf ball is very fast. So the next question is, does spin impact the distance a ball can travel? So let's look at some research by Opia et al. In 2010. Through calculations, this study managed to work out the height and distance a ball could travel with and without spin. So the launch conditions of this study were 15 degrees launch angle and around 100 miles per hour. And the ball with 0 revolutions per minute of spin traveled just under 80 meters, whereas the ball with 4,000 revolutions per minute traveled just over 120 meters. Now, based on this data, this shows that spin can increase the distance a ball can travel by around 60%, thus showing that spin is important to hit the ball a long way. Now, I'm sure you're probably wondering, well, why? Why does spin result in the ball traveling further? Now, I will answer this question, but in part 3 of the spin series, because first we need to understand the interaction between the spinning golf ball and the air. So let me explain this first. So let's firstly imagine a ball flying through the air with no spin. The air will flow around the ball and exit out the back, with the air above and below the ball traveling at the same speed. So now let's make this more relevant to golf. So let's assume the ball has backspin, which it will do when we hit a golf shot. The air will then be deflected in a downwards direction. Let's look at this deflection in a study that shows this. A study by Okia et al. 2010 looked at the aerodynamic characteristics and flow pattern of a golf ball with rotation. Now, the images you can see are adapted from this paper. The image on the left is a golf ball with no rotation, so 0 revolutions per minute, whereas the image on the right is a golf ball with rotation of 4,000 revolutions per minute. Now, the air is traveling in the same direction as I gave you in the example a few moments ago. So the air is traveling from right to left in both of these images. Now, as you can see from the wake that's created behind the ball, the image on the right is deflecting the airflow more than the image on the left, showing that the spin is causing the air to deflect in a downwards direction. So the question is, why does it deflect in this direction? And the reason for that is because the bottom part of the ball is spinning against the airflow, whereas the top part of the ball is spinning with the airflow. This means the air going over the top of the ball is going to be slowed down less compared to the air going underneath the ball. This is because when the air molecules on the top of the ball impact the ball is rotating in the same direction as the air molecules, slowing it down less. Whereas on the bottom of the ball is spinning in the opposite direction to the air molecules and therefore slowing the air down more. This means the air traveling over the top of the ball is traveling faster than the air traveling underneath the ball. This results in the air molecules that are going below the ball to detach much more easily from the ball's surface compared to the air molecules that are going over the top of the ball, meaning that the air is then deflected in a downwards direction. So let's once again look at the adapted images from the Okia et al. Study to see if we can see these differences in airspeed and separation. Now, the color on these images represents the velocity of the airflow. So when the air is closer to a red color, it's therefore traveling at a higher velocity, and when it's more towards the blue end, it's traveling at a slower velocity. So when looking at the image on the left-hand side here, the ball with no spin, we can clearly see that the airflow is traveling at similar velocities over the top and underneath the ball, because the shade of orange is very similar above and below the ball. Whereas when we're looking at the ball on the right-hand side, which has 4,000 revolutions per minute of spin, we can clearly see that the colors are different above the ball and below the ball. Above being more of a red shade compared to below the ball being more of an orange shade, meaning that the airflow is traveling faster over the top of the ball compared to underneath the ball. This means the airflow should detach more easily from the bottom surface of the ball compared to the top. And as you can see from the image, the separation point of the airflow is later at the top of the ball compared to the bottom, which is why the airflow is then deflected in a downwards direction. Now, because the air is being deflected in a downwards direction, there is a downwards force being applied on the air. And according to Newton's third law of motion, every action has an opposite and equal reaction. Therefore, the air must apply an upwards force back on the ball, generating lift. Let's also discuss Bernoulli's principle here. And this principle states that faster moving fluids exert less pressure than slower moving fluids. So in our example here, the air is moving faster over the top of the ball and therefore is applying less pressure than the slower moving air on the bottom of the ball. This difference in pressure results in lift being generated on the ball. To show the Bernoulli's principle, let's look at the adapted images from the Okia et al. Study. So the images show the pressure being applied to the ball. Again, on the left-hand side, we have 0 revolutions per minute, and the right-hand side, we have 4,000 revolutions per minute. And the colors represent the amount of pressure that is being applied. So if it's more towards the red end, it's a higher pressure, and if it's more towards the blue, it's a lower pressure. So when there is no spin, looking at the left-hand image, we can see the pressures on the top and the bottom of the ball are pretty similar. Whereas when we look on the right-hand side of the ball that's spinning, we can see that there is a lower pressure at the top of the ball because we have more of a blue color, and then at the bottom of the ball there is a higher pressure because we have more of a green. And this difference in pressure results in lift being applied to the ball, and we call this lift the Magnus effect. As you can see, backspin on the golf ball causes lift to be generated, and this lift is key to enable us to hit the golf ball a long way. Now, two questions currently come to mind. One, why does lift result in the ball traveling further? And two, if lift is so important for driving distance, why do we not maximize our spin rate to maximize the lift generated? These are 2 questions I'll be answering in part 3 of the spin series, so join me next time to understand more. So that's everything from me. If you liked this video, please give it a thumbs up, and if you haven't done so already, please consider subscribing to my YouTube channel. And all that's left to say is, I've been your host, Daniel Thompson, your caddy for all things golf science.